Welcome back. Remember we said there were three fundamental rules, counting rules, that underlie combinatorics, and in this segment we're going to introduce the second rule called the sum rule. As before, I'm going to introduce the rule formally, and at the same time I'm going to illustrate it with a concrete example. So the first assumption to apply this rule is that you're trying to solve a problem and you know of k distinct approaches for this problem. So let's say your problem is to find a flight to Paris. Well, one way you can solve this problem is to look for non-stop flights. So this is approach A sub 1. Of course, another approach is you could consider one-stop flights. That's approach A sub 2. And as a third approach, A sub 3, you could look for two-stop flights. Now, the second hypothesis for the sum rule is that each one of these approaches has different ways of being implemented. So approach A1 has N1 distinct ways of being implemented, and approach A2 has N2 ways of being implemented, and so on and so forth. So in our example, let's say you find 3 non-stop flights on the day that you're interested in. And then for approach A2, for the one-stop flights, you find 6 of those. And for the third approach, it has 7 ways of being implemented, meaning you find 7 different options for this approach. So now the question is, how many ways do you have for solving this problem? And the sum rule states that there are exactly this many ways of solving the problem. And remember, this summation notation is just the sum of all the n sub i's for I equals 1 to k, where k is the number of approaches. So in our example here, the total number of ways to solve this problem of flying to Paris is just the sum of 3, 6, and 7, which is 16 choices. So one important remark here about the sum rule is that the k approaches must be distinct, which means none of these ways of implementing the approaches must overlap. And of course, this is true in our problem because none of these 3 non-stop flights are one-stop flights or two-stop flights. In other words, these 3 sets of options do not overlap. They're completely separate and distinct. And that's built into the assumptions of the sum rule. Now, speaking of sets, as before, let me give you a second formulation of the sum rule in terms of set theory. Let's say you have k sets. These sets must be finite, and they must be mutually disjoint. What does that mean? That means if you take any 2 of these sets, these must be 2 distinct sets in the collection of k sets. The intersection is always empty. So this assumption is the same assumption I just mentioned, that these approaches must be non-overlapping. None of the elements of these sets must belong to more than one set. That's what it means. So how does the sum rule translate into set theory? Well, the rule says that the number of ways to choose a single element from any one of these k sets is what? Well, it's just the cardinality of the union of the sets. And in this case, because the sets are mutually disjoint, this cardinality of the union of the set is just the sum of the cardinalities of the individual sets. So again, to map this set theoretical formulation to our example, the set A1 would be the set of those 3 flights. The set A2 would be the set of those 6 one-stop flights. And the set A3 would be the set of those 7 two-stop flights. Since those sets are mutually disjoint, no pair of them overlap, the cardinality of the union of these sets is simply the sum of the cardinalities of the 3 sets, which in this case is 16.